From the soil under our feet to the stars above, matter makes up everything in the universe. Matter comes in 4 states: solids, liquids, gas, or plasma. In solids, molecules are tightly packed and maintain their shape. Add energy, like heat, and the molecules begin to separate and melt into a shapeless liquid. More energy, and matter turns into gas. Superheated gas becomes plasma, the 4th state of matter, where electrons tear away from their atomic nucleus and float freely around it. Even in cold climates, solids like this snow turn to water when heat energy pushes the temperature above water's melting point. Liquids can't hold solid shapes, but they do have volume and move to fill the space available, even space as big as oceans. While it's obvious that ice melts, even rock solids melt when they're subjected to enough energy. Rocks melted by the heat and pressure deep in the earth erupt from volcanoes as liquid magma and lava. Gas molecules are further apart and have even more energy than liquids. Gases, like air, and hydrogen gas in the universe have no fixed shape or volume. Superheated gases in the universe are plasma. Plasma makes up more than 99% of our visible universe. Its electrically charged particles are the stuff of stars. Physicist Albert Einstein came up with an equation, E equals mc squared, to help explain the relationship between energy and mass. The simplest interpretation suggests that matter can be converted into energy and energy into matter. The theory helps explain the curious beginning of the universe when an enormous amount of energy became matter. No matter what state matter is in, it demonstrates the property of inertia. This natural law means that matter doesn't change unless it's made to by some outside force. Ice may be moved to melt, and an avalanche to slow, only when moving forces, such as heat, act on them.
Physical properties of matter include melting point, boiling point, color, density, magnetism, crystalline shape, malleability, ductility, luster, and refractive index. The physical properties of matter can be observed without any change in the matter's chemical composition. Chemical properties, on the other hand, can be observed only when matter undergoes a chemical change. Here are some examples of chemical properties. Hydrogen peroxide decomposes easily into oxygen gas and water. Iron reacts with oxygen to form iron oxide. Sodium metal reacts with water to give off hydrogen gas. Sodium hydrogen carbonate, baking soda, reacts with acid to give off carbon dioxide gas. Lead nitrate reacts with potassium iodide to form a yellow precipitate of lead iodide. Red phosphorus can undergo combustion in air.
Hi, this is Matthew. Welcome to today's DMS StudyCast. A solution is the same as a homogeneous mixture because you cannot see the different parts. It all looks like the same thing. We are going to make a sugar-water solution. We make it by dissolving sugar in water. There are two parts to any solution: a solute, the sugar, and the solvent, the water. In a solution, the solute is the thing that gets dissolved. The solvent is the substance that is doing the dissolving. In this animation, you can see what happens to make the sugar dissolve. The sugar atoms are more attracted to the water than they are to each other. The water atoms surround the sugar particles and pull them away from each other. This continues until the entire sugar cube dissolves.
Hi, it's Mr. Anderson, and today I'm going to talk about solubility. To understand what solubility is, you first have to understand what a solution is. And so if you haven't watched that podcast, make sure you step back and do that. But solubility is a measure of how easy it is for a solute, in this case it would be table salt, to dissolve in a solvent. In this case it would just be water. And so the way that water dissolves a solvent, remember, or a solute, is that it'll actually surround the anions and cations inside that salt water. But solubility is a measure of how good it is at actually doing that. And so it's going to depend on what you're actually trying to dissolve. And so right here we've got a picture of a solute. We'll call that a solute sitting inside something that looks like a salt shaker. And then we've got solvent. And so in this case the solvent is going to be exactly 100 milliliters of H2O. And so if you look at this value over here, the solubility value for each of the different solvents is going to be a little bit different. And so the solubility value for salt is going to be 37.7. And so that means at room temperature, if you take 100 milliliters of water, you're going to be able to dissolve about 37.7 grams of table salt. Now if we compare that to sugar, you'll find that the solubility value is going to be much higher. Sugar, sucrose, is going to have all these hydroxyl groups around the outside. So you can actually take 200 grams of sugar and you can dissolve that in 100 milliliters of water, which is an astronomical amount. So you can get a huge amount of sugar mixed inside there. It has a high solubility value. If we compare that to something like baking soda, it actually has a value of around 10. And so it's hard to get baking soda actually to dissolve in water, and a lot of that has to do with chemistry. Remember, water is going to be a polar molecule, so it's really good at things that breaking down things that are charged. If we get something that's not charged at all, let's say talcum powder, you could try and mix it with water day and night, and you're never going to get it to mix together. And so if it's not able to mix, we call that insoluble. In other words, it has no solubility value, because it doesn't matter how much you add to it, water's never going to make a solution out of it. So we call that a low solubility value. Now, if I want to add more solute to water, one way that I can get more added to it is I can actually increase the temperature. And so this solubility curve actually has temperature on the bottom, goes from 20 degrees all the way up to boiling, 100 degrees on this side. And then on this side it's got the solubility values. So solubility values, which is the grams of solute for 100 grams of water. And you'll see that there's going to be a curve for each of the different salts. Now, why is it that if we heat up water it's able to dissolve material better? Remember, the way temperature works is that temperature is essentially how fast the molecules are moving around. And if they're moving around more quickly, they're more readily able to surround that salt. But it's not always exactly the way you might think. And so if we look at something, for example, here like potassium nitrate, you'll find that its solubility value down here at a really cold temperature is actually around 30 grams, but as we get it way up to near boiling, we can get that number up near 200. And so that makes sense. But if you look at some things, like here's sodium chloride, so that's just regular table salt, you'll find that its solubility curve is actually relatively flat. And that means that if you heat up water, you're not going to be able to dissolve much more salt. There's kind of a limit to that. And so that's dissolving solids or solutes in water. So what is saturation? Saturation is a measure of the point at which we reach where you can't dissolve any more solutes inside it. And so in this picture right here, we've got two phases, which is pretty cool. Up here we've got actually the phase between this sugar solution and the air. And so there's going to be movement, and so each of these particles that is a hollow circle with an arrow attached to it is going to be gas. We can think of that as like oxygen or nitrogen or air. And so that's going to be moving into and out of solution. In other words, some of it's going to be moving out into the atmosphere and some of it's actually going to be dissolved inside the liquid. And then at the bottom we've got some sugar cubes in here, and some of that sugar is actually becoming into solution and some of it is moving out of solution. And so the point at which we reach a saturation level, it means that we've added the most. And so let's just kind of think about this area down here. We've got sugar that we've added to it, and so up here we have an aqueous sugar solution, so it's sugar water. And so we have so much sugar down here in the bottom that eventually you get to a saturated point. It's the point at which you can't have any more sugar enter into the solution. Now, it doesn't mean that no more sugar is moving across. It means that it's reached this equilibrium when the movement into and out of solution is actually equal. And so when it does that, we reach something called a saturated solution. And so unsaturated is when we could actually add more to it. Saturated means you can't add any more to it. So you might be thinking to yourself, well, I understand what saturated is, but what is supersaturated? How could I ever add more solvent to the, or solute to the solvent than can actually fit? And so you have to think back to the slide before this, and that was, remember, we can actually increase the temperature, and if we increase the temperature we can add more solute to it. And so you can imagine if I increase the amount of heat, I can actually get more solute to absorb into the solvent. And so this is a pretty cool demonstration. What they've done here is they've taken sodium acetate, they added it to water, and they made a sodium acetate solution, but then they heated it up, so they got it really, really hot, and they were able to add more and more and more of that solute. It then became supersaturated when they let it cool down. In other words, there's more solute in here than it should be able to dissolve. And so the cool thing is you can add a crystal, and if you add a crystal of sodium acetate, you'll get this beautiful crystals forming, and eventually all that's going to come out of solution again. So it's going to go back to a saturated point where it's at equilibrium. Now, what's a fun way that we can actually play around with supersaturation? That's how we make rock candy. And so what you do is you heat up water, you get sugar to dissolve inside it, and then you cool it down, and we can put something like a stick or a string inside it, and then if you let it sit long enough it'll actually crystallize. And so that's a supersaturated solution, but we're getting those solutes to come out of solution over time. Next one is gases, and gases kind of flows in the opposite direction. And so remember, in a solution, let's say carbonated water, what you have is water, and then there's carbonation, or there's going to be carbon dioxide gas that's actually absorbed into it. So it's little bubbles inside there. Now this works a little bit differently. If you remember back when we were talking about solutes, as we increase the temperature, we were actually able to absorb more of those solutes into solution. Gases work in the opposite direction. As we heat up water, you can actually hold less of that inside there. What's an example of this? Well, there's a really good life example of this. And so this is a Elodea plant. But essentially what's going on is that this plant is putting oxygen bubbles into the water. And the amount of water that you get, the amount of oxygen that you get inside the water is called the dissolved oxygen rate. And so if you have a fish tank like this, and it's got a fish inside it, what's the fish actually breathing? The fish is actually breathing dissolved oxygen. So it's not breathing, for example, the H2O that is sitting inside the tank. Let's get a little bit of water in here. It's actually breathing the oxygen that is dissolving. So it's the oxygen from the atmosphere that's actually dissolving inside here. And so how do you get more oxygen in there for your fish? Well, you could put a bubbler in your aquarium if you ever had one of those. And what that's going to do is it's actually going to add air, and it's going to add bubbles to the water, and so it's going to increase the amount of dissolved oxygen. The problem is this: as we heat it up and we get hotter and hotter and hotter, the water can actually carry less of that dissolved oxygen. And so as you get hotter and hotter and hotter, you have this problem. You have one of all, the fish, and as you heat up the water inside the tank, the fish's metabolism is actually going to speed up. And the other problem you have is when it gets hotter and hotter and hotter, it can't carry as much dissolved oxygen. And so where do we see this as a problem? Well, you could see it around the globe. And so lots of times we tend to think that the most lush areas on the planet are going to be those right near the equator in the ocean. But actually, if you look at the dissolved oxygen levels, we're going to have way less oxygen here. And so where do you see the most life in the ocean? You see the most life in the ocean where you have cool temperatures coming from the south, and then you have enough sunlight at the equator. So we visit the Galapagos Islands, which are right here, and it's a great place because you get this cold current coming up from the south, which is actually carrying a lot of oxygen. It's also carrying nutrients with it, and then you get a lot of light up here as well. Where can this be detrimental? Well, let's say you build your power station right next to the ocean, and one way to get rid of that extra heat is actually to use the water from the ocean to cool it. This is actually a power plant that's located near San Francisco. As you pump that water back into the ocean, it's increasing the temperature, so it's decreasing the dissolved oxygen level, and it's really hard for fish and marine life that live right around that area, because not only are they speeding up their metabolism, but there's not enough dissolved oxygen for them to actually respire. So that's a double trouble. And so that's solubility. Again, a measure of how easy it is for solutes to be measured in solution. Thanks.
If you're not part of the solution, you're part of the precipitate. What is a solution? Well, in simple terms, a solution is just nothing more than a homogeneous mixture of a solute dissolved into a solvent. Well, that answers all your questions, right? Bye! Just kidding. A solution is what you get when you take a substance and put it in with a solvent. A solvent which can rip apart the attractive forces between the solute particles and disperse them evenly into a mixture. That's why it's called homogeneous, because all the particles are spread out evenly throughout the entire mixture. Here, for example, we have some sodium chloride, some positive sodium ions and some negative chloride ions. That is the solute. The solvent is the water. Now, why can water dissolve salt? Here's why. Salt is made of positive and negative ions. Water, being a polar molecule, has partially negative and partially positive ends. Therefore, the partially negative end of the water molecule, the oxygen end, is attracted to the positive ions, specifically the positive sodium ions. That's why we have the sodium ion and these oxygens surrounding it. The partially positive end of the water molecule, the hydrogen, is attracted to the negative ions, which is why we have these negative chloride ions with the hydrogen end of the water molecules surrounding them. Water molecules attach themselves to the ions, and because water molecules are constantly moving, their motion will actually cause the ions to separate from each other and pull away, dissolving. How much can you dissolve? Well, it depends on a couple of things. First of all, how many water molecules do you have? Because the more water molecules you have, the more stuff you can put into it. Also, how fast are the water molecules moving? Because the faster they're moving, the fewer water molecules it's going to take to tear the ions apart. So there are a few factors that can affect how much can dissolve. Because the particles are dispersed on the atomic or molecular level, there's no filter paper that's small enough to stop the particles from going through it. You cannot separate a solution by filtering it, because the holes in the filter paper are just too huge to stop any of these small particles from just passing right through it. Also, because the particles are so small and so far apart from each other, light can't reflect off of it. There's just nothing for light to bounce off of. I mean, you see this beam of light, right? Hitting the screen, you actually see the beam of light? Of course not, because air molecules are too small to reflect light. But if there's some dust in the way, you can see it. On the molecular scale, the particles are just too small to bounce light off of, which is why you can see right through a solution. They're transparent. Also, because the particles are dispersed evenly on the molecular level, it's homogeneous. And the only way you can separate a solution is by getting rid of the solvent. You see, salt has a very high melting point, about 1074 Kelvin. Water, though, boils long before that. Water boils at 373 Kelvin. So if you heat this mixture up, when you hit around 373, it's actually going to be a little higher than that because of something called colligative properties. We'll look at that later. The water molecules will have enough energy to escape and break free. And when you evaporate or boil off the water, all that does is leave behind these ions, which are attracted to each other, and come back and reform the original solute. So you can separate a solution by evaporating or boiling off the solvent. Now, if water didn't have partially positive and partially negative charged ends, there'd be nothing to attract these positive and negative ions. In order to dissolve things that have charge, your solvent needs to have charge. In other words, like dissolves like. Polar solvents, like water, are capable of dissolving things that are charged, like ionic compounds and other polar molecules. However, as you know, water and oil don't mix. It takes a nonpolar molecule to dissolve a nonpolar solute. For example, this molecule here called benzene, look how many lines of symmetry this thing has. I mean, it is loaded with lines of symmetry. It's just crazy with them. You could say, actually, this is like one of the most ultimate nonpolar solvents. It's so nonpolar, it can even dissolve plastic, which is also nonpolar. This is carbon tetrachloride, which is also a nonpolar molecule. Carbon tetrachloride was used in the dry cleaning industry, except they found out that it was carcinogenic. And, you know, if you can get cancer from washing clothes or wearing clothes, probably not a good thing. Nonpolar solvents are very handy to use in glues that are meant to hold nonpolar things together. So polar things can dissolve polar things, but nonpolar things can't dissolve nonpolar things. That's why you can pour water into a plastic cup and the plastic doesn't dissolve, because the plastic's nonpolar. Now, how much solute can you dissolve in solvent? Well, like I said, it depends on how much solvent you have. Reference table G gives you the solubilities of different kinds of solutes at different temperatures, assuming you have 100 grams of water. If you have 200 grams of water, then you just double all the values here, because 200 grams of water can obviously hold twice as much as 100 grams of water. So holding the grams of water steady at different temperatures, we can dissolve different amounts of different solutes in that 100 grams of water. Now, there are two things that we need to look at. Entropy being the most important. When you dissolve something in water, its entropy will either go up or down depending on what phase it is that you're dissolving. If you dissolve a solid into water, the solid becomes like a liquid when it dissolves. Therefore, its entropy increases. This is favored at high temperatures. Increasing the temperature on a solid solute is going to increase its solubility. But for gaseous solutes, Gases already have high entropy. When you dissolve them in water, they act like a liquid. You're bringing their entropy down. That's not favored. Therefore, this will only be favored at low temperatures. Lower the temperature, increase the solubility. And so you can see what we've got here. The curves that go up are solid solutes, and the curves that go down are gas solutes. HCl, hydrogen chloride gas, gets less soluble as you increase the temperature. Why? Because its entropy change is not favored. And the higher the temperature, the more unfavored it is. Here, for sodium nitrate, which is a solid, when you dissolve it in water, its entropy change is favored, going up in entropy. And increasing temperature just makes it even more favored. So solids get more soluble as temperature increases, and gases get less soluble as temperature increases. So what's another way you can get a gas to dissolve in water? Change the pressure. If you increase the pressure, you will force that gas to dissolve. Increase the pressure, you will increase the solubility. This is why when you open up the top of a bottle of soda, the CO2 comes out. Not because the CO2 is just sitting there waiting to escape, but because when you lower the pressure,